Hi, good evening, everyone. Thanks for joining me today for the chemistry practical webinar. All right, it's 7 o'clock. I hope all of you have your dinner. Otherwise, you can have it in front of the screen. But what I also hope you have is the materials for today's session. Okay, so if you do not have the worksheet link, right, are you able to help send the link? Because I don't have the link right now. Do you have it? Yeah, so for those who have it, I hope you have printed it out. Otherwise, you can also use a soft copy. Okay, you should have received it when you registered. But there was also an email that that was sent to you that mentioned that the link has been ready. Is ready. Okay, otherwise the link is here. Okay, you can download a soft copy. Okay, so we'll be using that for today's lesson. Now, I'm sure you know, right? Your prelim is coming soon. Your prelim practical for chemistry, for your sciences, they're all coming soon. Okay, so this should help you prepare for it if you have not. Okay, so thanks for joining us today. I'll be providing a lot of information, tips, and how to do all these questions. Okay. Later there will be another teacher Ashikin. She'll be joining me a bit later because she has a class right now. Okay, so I hope all of you have gotten the materials. Okay, so the link is in the chat. So if you do not have it, feel free to just access that and download. Okay, all right. So I'm gonna begin. Okay, let me begin here. Share my screen. So we're covering quite a number of things here. All right, so first thing is to talk about your assessment objective. Okay, just the beginning, right? Then we talk about recording readings, graph, titration, QA, planning. Okay. Now, you must definitely know what are the things that are testable for practical. Okay, you cannot go into the practical but not knowing that what can be tested. I'm sure you know maybe like titration, QA can be tested, but there can be a lot of other things that can be tested. Sometimes they like to test funny things. Okay, just be prepared for something different. But definitely those that are very common, you want to be sure to have tried it in your school. Okay, for today, of course, we can't do all the hands-on, but we are preparing for all the theory part of that. Okay, so for whatever recordings, we will provide you with some data. Okay, then we'll do all the theory because you must know practical is not just about doing the experiment. You need to observe, you need to record, you need to analyze, you need to draw a graph, okay, etc. And then plan your experiment also. Okay, so these are the topics that you want to study. Okay, so when we go for practical, doesn't mean that there's nothing to do with your theory. Actually, they're all related. Of course, there must be something that you have learned before in your theory, and then they can then test you in the practical. Okay, so still important to get your theory concept strong. All right, so go revise on some of these things as well. Okay, so separation techniques, mole concept calculation, your preparation of salts. This applies only for pure chemistry students. May I just know how many of you are combined science students? Just raise a virtual hand. Combined chemistry students, anyone? Okay, one, two. Okay, so most of you are in pure chemistry. Thank you very much. Yeah. So there will be a few things that are okay. I will say actually for practical, they are quite similar. They are quite similar. Last time it used to be pure chem, most likely is do titration and combined science is do QA. But nowadays it's not so fixed anymore. Okay, they can switch around, play around with the different experiments. All right. So for pure chem, I think the difference in syllabus is just the preparation of salts. Okay, so that is one topic that you can go through that. And then QA, redox, reactivity series, okay, speed of reaction, as well as some organic chemistry. Okay, these are just the topics. So you go through the theory, all right, just to prepare for the different types of topics that will come out. Okay, these are the dates for the O-level practical. Okay, so do take notes for chemistry, physics, biology, or even combined science. Okay, this should be the latest dates, but I hope you all refer to the actual timetable if there are any changes. But this one was referred to it at the on 14th of July. Okay, quite recently, so I don't think there's a change. Okay, so very important points: entry proof, your IC, and definitely stationary. You want to draw graph, you need calculator to do a calculation for titration. Okay, your rulers, make sure you have all this. Okay, you can take note, you can take a screenshot of all this. Right, I don't think this is in your document. Yeah, for those who have just joined, if you do not have the material, please, the chat already has the link, right? Feel free to access that and download and use the materials, okay? Now, as I go through the content later, any question just put in the chats, all right? All right, I'm going to move on and start. Now, I have put here the assessment objective and the weighting for all the practicals, be it pure or combined science. Okay, so for pure, it's paper 3, it's a bit longer and more marks, higher weighting. Okay, for combined, it's lighter. Okay, essentially, the experiments cannot be too different. I mean, the type of question that they can ask cannot be too different, but the papers are of course not the same lah. Okay, so you still want to do well because this practical, for pure is 20%. So that's quite a huge percentage. It can really affect whether you get your A1 or not. Okay. So of course, whatever instructions they give you in the questions, make sure you follow, use the correct apparatus, use the correct instruments. Okay, and of course you must already know some of the things. For example, precision, which we will cover later. Okay, color of the solutions, make sure you write correctly, right? And do not produce fake results or anything. Okay, and you will also need to think about possible improvement. That is part of evaluation. Okay, so you do the experiment, think about how can you improve the accuracy of the experiments. Okay. Uh, okay, is that the link for PSLE math? Okay. Right, can you check the link again? I'm so sorry about that. Okay, yeah, here for chemistry, yeah? All right. Okay, now, so definitely, you must know that for QA, by right, for theory paper, your paper 1, paper 2, you must remember your QA observation and colors. Okay, but for practical, these are provided. Okay, these are provided in your question paper. So there's no need to memorize, but of course, I will still suggest that you know some already. Okay, so you don't spend so much time flipping to the back and try to check which is the correct color. Okay, because you might be a little bit stressed during the practical. Okay, uh and you might you might flip all the way to the back and then you fumble around. Okay, so if you can remember some of these, that will be better. But of course, feel free to refer to it just to confirm. Okay. Now, simple calculation, definitely your mole concept calculation must be strong. Okay. You remember, yeah, I'm sure you have done titration calculations, so all these are important. So these are all the formulas that you can use. Okay, I will not go through them. Later we'll go through the question and we'll use some of these. Okay. Right. Now let's start the lesson proper. Okay, first thing is on recording readings. All right. Very common instrument or apparatus that you will use in the lab. That will be those that I have highlighted here. Okay. Stopwatch, measure time, electronic balance, or mass balance. All right. Pipette, burette for your titration. Okay. So you need to know the precision of all this. Stopwatch is only measured up to 1 second, but of course depends. The stopwatch precision can be different. Okay, really depends on what they provide you. Likewise, for the thermometer, some thermometer is 0.1, some thermometers are 0.5. So depends on which thermometer they provide you during the in the lab. Okay, electronic balance 2 decimal places only. So when you record, okay, depends. Okay, again, electronic balance also depends on the apparatus they give you the balance. Okay, but usually it's 2 dp. Okay, so if you see more than that, you keep it to 2 dp. Okay, pipette and burette, I hope you already know them. Okay, pipette only one fixed value and it's always 0.0. one decimal place. Burette, two decimal places. All right, and its precision is 0.05. So when you record for burette, it's always a 0.00. The second decimal is 0 or it's a 5. Nothing else. Okay, there's no 13.17. Okay, it's not that precise. Okay, so it's 0.05 or 0.00. Okay, now whenever you need to record any values, any quantity, make sure there is a unit, especially when you need to draw a table. Now the units should be placed at the top, the header, the heading of the column. Okay, so you should write like mass slash grams or time slash second. Okay, so the unit must follow, but you put it right beside the quantity. Okay, this should be in the header. So, and not, you don't write for every row, you go and write something gram, something gram, something gram. Yeah, don't do that. The unit is all the way at the heading, then you just record the values that you see in the respective boxes. Okay. Now, for the significant figures, okay, number of significant figures given for average and difference should be the same as what was measured. Okay, so for example, when you measure you measure the volume using a burette. Okay, so how many significant figures is that? And then what you calculate would in terms of average and difference, they should be kept the same. Okay, but any calculated quantity, take note, there's a difference here. Number 5 here is talking about measured, what you have measured using the instrument directly, like burette, thermometer, etc. Those are measured quantity. But if you use this measured quantity and do a calculation, like for example, you need to divide by time for some reason, then those must be in 3SF, three significant figures. Okay, so later we'll try some data manipulation. Now, just one quick question. Now, let's say this is the stopwatch you use in your science lab, and it records like this. What would you record? Now, remember, this is a stopwatch. Unit is in seconds. What will you record here? Just put in the chat. Good. I see a number of answers, and they are quite different. Okay, I don't know why there is 1 second. Okay, this is 1 minute. Okay, you look at the position. Okay, maybe I hope it's not too small. Let me zoom in a little bit here. Okay, this is 1 minute, 20 seconds, and then there's a 73 there. Now, how many seconds is this? So 1 minute, you need to convert that to seconds. Okay, so that is already 60. So you don't record the minutes because we want the SI unit which is seconds. Okay, so that would be at least 80 seconds. But do we need the 73? We don't use milliseconds. Okay, we don't need that because we record stopwatch to 1 second. Okay, so keep to that. We record it to 1 second. That means that this will just technically be 80 seconds. That will do. Okay, so you can ignore the 73 and do not go and round it up. Okay, it is not 81 seconds. You don't round it up, these values. Okay, whatever you see here, 80 seconds, you leave it as that. Do not round up a measured value like this. Okay? And alright, so you want to take notes. First thing, for stopwatch in seconds. Second thing, do not round it up. Okay? Alright, let's move on to question A here. Now, question A, you are given powdered chalk, which is basically calcium carbonate. But this is an impure sample. Okay, it's an impure sample. So you want to take note that we are trying to find the percentage by mass of calcium carbonate. Okay, we don't need to be too concerned about the impure or percentage by mass. Main thing for this question, we are talking about how we manipulate the data. Okay, how we record the data, the readings. All right. So what we need here, we are given X, which is 1 mole per dm cube hydrochloric acid. Okay, and C is 0.60 grams. X is this. X is the acid. Okay, so we're going to measure the loss in mass. So let's say you have done this experiment in the lab. Okay, they give you this set of instructions. You try to follow. Now we are given 50 cm cube of measuring cylinder to add 50 cm. So this is the measuring cylinder. We're adding 50 cm cube of X into the conical flask. Okay, so we add that. Then we weigh. Now take note of this word weigh. When they say weigh, that means that you have to record, right? Because you weigh something, you must record down. Likewise, at the bottom here, please highlight these two words, reweigh and record. Now, so these are the data you need to record down below. Okay. Now, do take note that this conical flask and X, right? That is the first reading. Then second reading, what do we have? We have conical flask and X plus all of sample C. So once we have added sample C, we swirl it until reaction is complete. Now, because for this reaction, you must know that it's an acid-carbonate reaction. And the only way to know when the reaction is complete is when there is no more effervescence. Can anyone tell me what is this effervescence? You should know, based on your theory, you should know. Thank you, Isan. Yes. Great. Yeah. So I think all of you should know, right? Okay, so even if you do not know, now, I mean, if you do it in the experiment, they tell you this is solid A, this is liquid B, you mix them together, the first thing you see is effervescence. And how will you know the reaction is complete? Of course, when there's no more effervescence, okay? So you don't even need to know what is this reaction. Based on the experiment itself, once you mix them together, there's effervescence, that means something is happening. And when there's no effervescence, it stops, then your reaction is complete. Okay? Now, so once that is done, we reweigh and record the mass. Okay, record it in the appropriate format. Now, so I need all of you to draw this table below. I think it's blank for yours. So let's draw it out nicely. Okay, if you don't draw a table, fine. You write it out nicely. First thing, what do we measure? The mass of conical flask and X. That is the first thing you have measured. Can you write it down? That is the first thing. Second one, conical flask and X with sample C. And that is until after the reaction is completed. Okay? Yes, carbon dioxide, correct. Okay, remember, so electronic balance, how many decimal places should we record up to? If we flip back to the previous page, how many decimal places should we record up to? 2 decimal places. Thank you. Yes, 2 decimal places. So even though you see you go to the electronic balance, okay, you queue up for it, and then you measure that. You see 3 decimal places. You don't go and record all 3. Record only 2 decimal places. Thank you, Shuhui. Thank you. Yes. So 2 decimal places, right? So take note of that. So which means that the first one is recorded as what? Mass of conical flask and X. Again, right, we do not round it off. Just now I mentioned for the stopwatch example, even though there's an extra decimal or a smaller quantity, okay, do not go and round it off. So we just basically just ignore that value. All right. Do you have it already? What are the masses here? Can you let me know that you record down? I've already given the hints, huh? Okay, come and let you all submit your answers in the chat. Okay, please try. Please try. It's okay to get it wrong. I don't know to see what you all think. Okay, you see, I'm seeing a few mistakes already. Okay, I'm seeing a few mistakes. Do we round off? I mentioned we should not round off. Okay, that's why there's a reason why this is 7. See, should I round off? No, don't round off. Leave it as take it as though this 7 don't exist. It is just 172.91. Because if you round off, it deviates more from the actual value. Okay, so do not round it off. Right, so you should be recording 172.83 and 172.91. Okay, and common mistakes are already seen. Some of you record all three decimals, some of you record rounded off values. Okay, now one more thing that I want to highlight is, okay, just now I mentioned about the units here. So units already in the header. All right, so you don't need to put the grams in your readings. Okay, so take note of all this, all this are important. Yes, thank you. Thanks for all your responses. Yeah, great. Okay, let's move on. All right, so now the question is, why is the mass of gas lost? Now be very careful here. I want you to try. Think about it. Okay, it is not simply just these two values. That's my hint to you. If you are confused, you read the whole question again. Okay, my hint is that it's not just simply these two values that you see of the conical flux, that you see of the electronic balance. Does anyone have the answer? Hmm. 12.3 dm cube. Review, we're asking for the mass. We are not looking for volume or percentage. We are just finding the first thing, mass loss. Okay, mass of gas lost. That's all. Okay, we are not going to answer the question fully, which is percentage by mass. First thing is to find the percentage by mass, we need to find out how much gas is lost. Okay, and the way to do it is to measure these two mass here. One is before adding C, one is after adding C and after reaction has completed. So what is missing? Great. I'm seeing a few correct answers. What about the rest? If you simply minus off, then it's just a 0.08, but that's not the answer. Okay, I shall not wait further. Also not a 0.02. Okay, you must understand, right? This second value, here, 172.91, is of course after adding C, but also after losing the gas. After losing the gas. Okay, so this is the final one without carbon dioxide anymore. Okay, what is our initial mass once we added C? What is the mass of C that we're actually adding? C is a 0.60 gram. So we are adding all of sample C into the conical flask. So which means that conical flask plus X plus C is 172 here plus a 60.0 grams. Okay, that is conical flask plus X plus C. Then we minus off the second value. That is the mass of carbon dioxide that escaped. Okay? Yes, yeah, correct. Right, so take note here, don't forget about the mass of C that should be included. Okay? So here, right, so what happens is, okay, if if you have used the rounded off values, then you end up with maybe 0.51. Okay, but since I already mentioned, don't round it up, so you should not be making this mistake. Okay, or you have used the 3 decimal places, then you'll get the wrong values. Okay, so it's 0.52 grams. All right. Any questions on this before I move on? Okay, let's move on. All right, next question, question two. Now, this is a very common question. You actually see this question, this type of question, very common even in your paper two or even paper one. Okay, sodium thiosulfate solution with acid. And what we get here is a precipitate. And I think you all should know the precipitate here. Okay, and what we will observe is the white precipitate in the conical flask or the beaker. Okay, maybe I just show you this video first. Okay, so that was a very short video to show you how the precipitate forms and when you stop your stopwatch. Okay, you can see that the mixture turns cloudy quite quickly. Within 30 seconds, you could really barely see the cross underneath the flask. Okay, so this is what this experiment is about, and I'm sure you have seen this question in your theory, or maybe you have even tried it. How many of you have tried this experiment? No? No one? Okay, I think some of you have tried. I think your school, some of your schools might have tried these experiments, or maybe you have tried it yourself. Okay, so this is a very common one. All right, so we are using sodium thiosulfate with hydrochloric acid. So these are the steps we have. We need to use a 10 cm cube measuring cylinder. We label that as A. Now, so we use this measuring cylinder to add 5 cm cube of A into a beaker. Okay, then we place a card with a cross on it behind the beaker. Okay, so similar to what is done, either behind or underneath it. Okay, then we use another measuring cylinder. This time around is 50 cm cube. We add 10 cm cube of B, then we add 35 cm cube of deionized water. Yeah, this session will be recorded and uploaded to YouTube. Yeah, so not to worry. If you miss any of these, you can refer to the YouTube or you need to review it. Feel free to do that. Okay? Yeah, or at the same time, you can also screenshot if you want to, right? Okay, so no worries about that. Yeah. Yeah, so coming back to this, 5 cm cube of A, 10 cm cube of B, and 35 cm cube of deionized water. Now, for this B and water, they make it 45 in total. So can you see that we have made the total volume 50 cm cube. Okay, So they're gonna pour this B mixture of B and water into the conical flask, basically the beaker. I think this is the beaker. Can you please change this? The beaker where A was in. Okay. And then start the stopwatch. Alright, so immediately start, and then the moment you can see the cross, okay, then you stop the stopwatch. Okay. Now then we'll repeat the experiment for 2 to 5 using different volume. Okay. So if you look at the table below, we have some values for you. So experiment 1 was 5, 10, 35. That makes up 50 cm cube. And we want to keep the total volume of this mixture the same. That's why the ionized water must be added. Okay, so volume of A is the same. We have increasing volume of B, 20, 30, 40, and so on. And the ionized water added to make the total volume constant. So that is fair. Okay, so can you help to fill up the two volumes here for experiment 4 and 5? Okay, so take a few seconds to fill up 4 and 5 just on the volume of B and deionized water. Okay, it just give you a few seconds. Itasha, yeah, question 1. Yes, which part do you need? Let me zoom out a little bit. This part? Done ready, Itasha? Yes, great. Thank you. Thanks for the volume. Correct. I am assuming you are done, Itasha. Okay, so let's coming back here. Correct. So the volume here is 45 and 5. Okay. Remember, we want to keep the total volume the same, so that is a fair comparison. Okay, for a fair test. Now, before we talk about concentration, let's come back to the top here. I mean, not the top, just above that. So we have the rate of reaction, okay, given in this equation. Rate of reaction is 1000 divided by reaction time. Okay, so this reaction time is what you will measure using your stopwatch. Rounded off to the nearest second. No, sorry, not rounded off. Recorded to the second. Okay, not rounded off, recorded to the second. Okay, now can you help me fill in this rate of reaction? Remember this rate of reaction, you must record it, yeah, you must calculate it up to 3SF. Okay, because just now I mentioned what? Measured quantity, stick to the same SF, okay, as what you have for your instrument, but calculated quantity, you must round it off to 3SF. Okay? So rate of reaction is a calculated quantity. Okay, Kaden, to answer your question, should you wash it with tap water, deionized water, or the solution to put in? Usually, definitely if you talk about titration, which we'll cover later, a bit more specific later, the burette, the pipette, you must wash with deionized water, then wash with the solution that you're going to fill it in. Okay? For conical flask that is below the burette, you only wash it with deionized water. Okay, deionized water is enough already. You don't need the tap water. Okay, deionized water is fine. Yeah. Then you don't wash it with any solutions for conical flask. Okay, but for any other random question, if they just say that add a burette, okay, in this case, are we using burette? No, we are not. Okay, but for titration, it's definitely those few steps. Okay, burette, pipette, wash with DI water, then the solution that they are supposed to contain. Yeah, if the solution is not enough, you can definitely ask for more. So just raise your hand, then inform the teacher that you need more. They will give it to you. Okay? Yeah. Don't be afraid to ask the teachers, because you are supposed to be provided the solution. So not to worry about that. Okay, let's come back here. Thanks, Yang. Let me check. Now, record to 3SF, Yang. The first one, the second last one, not 3SF. Okay, so I think most of you should have pressed your calculator. Now, do you get this? Okay, so the first one, you do not round to 6.7 or 6.667. It has to be 3SF. So 6.67. Okay, then this fourth one, it should be 25.0. It needs that point 0 to make it 3SF. Okay, so common mistakes made by students. Right? Other than that, I think the rest are fine. Okay, now coming back to concentration. So how do I calculate the concentration? Now, why we need to find concentration is because we need this for the graph drawing, which is next. Not for this question, but for this question, this question was actually an actual O-level question, but modified. Okay, they tested something like this, and they used the concentration. So you need to know how to calculate the concentration. Let's say if it comes up again. Okay, and definitely you must know how to calculate concentration for your mole constant and stoichiometry also. Okay, so concentration of B in mole per dm cube. First thing, what is the initial concentration that was given to you? 0.50 mole per dm cube. Okay, that is the initial standard solution that they have given you, but you have only used 10 cm cube of that. Okay, you try to understand this. You are given this 0.50 mole per dm cube standard solution of sodium thiosulfate, but you have only used 10 cm cube of that. The concentration is still the same, That 10 cm cube is still the same, but don't forget you have diluted it with 35 cm cube of water, making the total 50 cm cube. Of course, including the volume of A lah. Okay, so now your volume is 50 cm cube. Okay, but in order to calculate this current concentration, you need to find number of moles. You have extracted 10 cm cube from this solution, 0.50 mole per dm cube. How many moles are there? Okay, so this goes back to your mole concept. Of course, you can use this equation. You can use the triangle method or just the formula itself, up to you. All right, I want to find the number of moles. So that means that it will be concentration multiplied by volume. Okay, what's our concentration? 0.5, which is given here. Volume, 10 cm cube. But can we use 10 cm cube? What should I do to this 10 cm cube? Tell me, what should I do to this 10 cm cube? When you do a mole concept, what's this thing that you always must do? Yes, divide by 1,000, which means you convert it to dm cube. Okay? How does deionized water increase or decrease concentration of B? Now, because okay, understand I have this concentration that is given to us. Okay, but I only use 10 cm cube. Then I added deionized water. I'm diluting this solution. So that concentration has changed. It's more diluted now. Okay? Okay, like what some of you said, you convert it to dm cube. Okay, so that is 0.01. So you should get 0.00500 K3SF. Take note of the number of zeros you have. So I think Ziyang, your number of zero is wrong. Yeah. Okay. So this is the current this is the number of moles that you get from the 10 cm cube. And you have now diluted it. Total volume is now 50 cm cube. And then you find your concentration. You have the mole, you have the volume, which is 50 cm cube. Then you can find your concentration. Okay, so which is simply mole over volume. All right, so it's 0.100 mole per dm cube. Okay, Can? Yeah, so you do the same for the rest. Okay, maybe I just give you a minute to fill in the rest. Then I will show you the answer. Okay, just to let you try out the calculation here. Use a similar method. Okay, concentration times volume first to find mole. Then use that mole divide by the current new volume, which is 50 cm cube. Okay, so just fill in on your material itself. Then later I'll show you the answer. Okay, do it quickly, because I want to move on to the next part already. So all this we are doing recording data, data manipulation, okay, and taking note of your precision, number of decimal places, number of significant figures. I think we have went through all that. Okay, so you want to practice on some of this. If you need to review again and again, please do so. Okay. Okay, I'm going to flash the answer. Actually, there's a trend if you realize. You don't really have to calculate it. Once you calculate one or two, right, you more or less see a pattern. Like for example, they are all proportional to the volume of B, right? So 10 cm cube, 0.1, 20 cm cube, 0.2, 40 cm cube, 0.4. Yeah, you can see a pattern, but of course, calculation gives you a confirmation. But observing and analyzing your results give you an edge. Okay? Can I? Okay, I'm going to move on to graph drawing. Now, graph drawing, you should be familiar. You've done it in mathematics, physics, chemistry, and all other subjects also. Okay, so I'll go through important points here. You should definitely already know independent variable, which is the change variable, drawn on the x-axis, horizontal axis, and y-axis is the dependent variable, what is being measured. Okay, all your axes should be labeled. Units must be provided, okay, with the slash. Okay, if it's red, it's slash second inverse. Okay, we don't use bracket anymore, not for secondary. Okay, now when you draw your graph, your scale is very important. Okay, so try to keep to at least half the grid. You must choose a scale that is appropriate, that can fill up at least half the grid that is provided to you. Okay, if you are not filling up at least half, then you have to choose a different scale. Okay. Do not draw zigzag line. Now, some of you, we have this habit of drawing zigzag line, which is not needed. If you need to start with a different value other than 0, just start with that value. Okay, don't go and draw zigzag line and then start off somewhere as maybe 50. Don't do that. Just start off 50 at the origin there. Okay? And of course, don't choose odd scale. You must choose a scale that's easy to read. Okay, don't use 1:3 or 2:3. These are very complicated and you get very confused and you don't even know how to measure one small square as how many. So choose values which are easy to read. Okay, so 2 centimeter, which is one big square, represent either 1 unit, 2 units, 4 units, 5 units, 10 units, etc. Okay, should be easy to calculate these values. Okay. And you should label your scale at every 2 cm, which is every large square, not every half a large square. Okay, or you can say, yeah, basically every 2 cm, okay? And don't use fractions. Now, usually, when you plot your graph, you use a cross. But I know some of you, you don't like to use cross, you use dots. Jolie, to answer your question, no, you don't always have to start with 0. Like I said, this point here, if a graph begins with a value other than 0, you start off with a value that is comfortable. Like for example, if you have a reading that is maybe 35, then the next one is maybe 38, then the next one maybe 42, and then it doesn't make sense to start from 0. You could start off with 30. So immediately, right? Okay, so let's say for example here, so with my example there, it could be a 30, 32, 34, 36, 38. So you don't have to draw zigzag line or what. just start off as 30, but label it clearly. Okay? Yeah. Okay, moving on. So for your graph, try to use crosses and of course use pencil, don't use pen. Try to use crosses because there can be more than one graph to draw. So if there's more than one set, then you have to use a different one. Use a dot. Okay? Then of course you must label each of them clearly. Okay? And it's very common to have more than one, especially for chemistry when you're dealing with temperature, they sometimes ask you to draw two graphs and see which one intersect one another. Okay? So bear in mind that. Hold on, experiment 5, is it? Yeah, the concentration is correct. 0.45, did I say 0.5? Is there anything wrong here, Ed? 0.45 mole per DMQ, right? You're right. I think you saw wrong here. Okay, so this experiment 5 is 0.45. Okay, nothing wrong, Coming back here. Okay, line of best fit. Now, I'm sure you all have drawn a line of best fit before. Very important point is make sure you have the same number I mean, as much as possible, you can pass through all the points, but usually you can't. You want to make sure that same number of points are on each side of the line or the curve. Okay? And it should pass through the middle. And there could also be best fit line that don't even touch any points. Okay? As long as your best fit line is positioned nicely, there's equal number of points above and below, it's fine. Okay? Will there be any swap of apparatus? I'm not too sure what you mean by swap of apparatus. I'm not too familiar with the physics part there. Maybe you can elaborate a bit more on that. Okay, now, yeah, so like I mentioned, line of best fit may not pass through any plotted point. So it's okay to not pass through anything. But it depends, it depends whether you need to pass through on the origin. I'll elaborate on that in a while. Okay? Now, if it happens that any of your reading is an anomalous point, you don't use it at all. Okay? The anomalous point, once you have drawn with a cross, and if it's anonymous, okay, then you draw a circle around that to show that you are rejecting the point and you will never use that for your best fit line. So you just ignore that and use the other points for your best fit line or curve. Okay, so don't use that. Now, you also do not want to extrapolate. Don't go and extend for no reason. Okay, so and once you have drawn until the last plotted point, just slightly extend it will do. Okay, don't go and draw like extremely extra. Don't extrapolate it. Okay, but whether or not it passed through your origin, this is a very important point. Okay, this is not in all of your document, so you may want to take a screenshot of this. Now, decide whether you need to draw your best fit line passing through the origin or not. Okay, it really depends on what you are measuring. For example, if you're asked to draw a graph of rate of reaction against concentration, if your graph passes through the origin, it means what? It means that when the concentration of that solution you use is 0, there is no rate of reaction. It must make sense, right? So which means that this graph has to pass through the origin. Because you're not even using any B, any concentration of B, which means that you're not using B at all, how would there be a rate of reaction? So these are times that you need to let it pass through the origin. So you can take it as the origin is like another point. So before you even start drawing, okay, you have all your plotted points, then you think about your graph. Is it supposed to pass through the axis? If the independent variable is supposed to be 0, how would the dependent variable be? Then if it's supposed to be 0 as well, that's when it passes through the origin. Okay? Let me look at some of your questions. Yeah, you can draw a curve actually. Now, some of you are asking what is a curve of best fit? Now, when you draw a best fit line, it can also be a curve. That's why you say a line or a curve. the question will tell you whether you need to draw a line or curve. But sometimes it's very obvious. You see your points is like it's curve. If you see your points are like this, then it has to be a curve. Alright, because it doesn't make sense. You draw a line, it's not gonna work because there will always be it's not yeah, it looks like it's supposed to be a best fit curve. Okay, so best fit curve is still the same thing. The concept is the same. You try to pass through as many points as you can. Okay, otherwise, make sure you have the same number of points above and below the curve. Okay, so that's the best fit curve. Extrapolate means is to extend the graph more than expected, like this. Like you have finished your reading at 5 here, you have no more reading, you don't need 6, 7, 8, 9, 10, you don't need all those. Then you go and draw your graph, extend all the way until the end of your graph paper. And then that is not needed. You don't have to extrapolate that. You don't have to draw extra. So once your reading is here, 5 cm, okay, then you can just extend your line slightly, and then you stop there. Okay, so don't go and extend. So the rate of reaction graph is, yeah, so you can draw a curve. Okay, if it looks like a curve, you draw a curve. And they should actually tell you if it's a curve lah. So you're talking about the swapping of the apparatus as well as some of the chemicals that they might give you. Yeah, they might swap it. They might swap it. Yeah, it's possible. It's just to be fair lah. It's just to be fair, so that there's no error coming out. Okay, so if something happen, you know that it's because of one set of instruments. Okay, yeah. Okay, so you all know when to pass through the point of origin. Okay, I'm gonna move on. Okay, calculating gradient. Now, this is basically the same as what you have learned in your mathematics class. Okay, you have your graph, go and find 2 points which are far away, but do not use plotted points. Okay, you must not be using any plotted points to find your gradient. So you choose 2 points on your graph, draw a big triangle. Okay, then use your rise overrun to determine your gradients. Okay, I think you all should be experienced in this. Okay, you all should be experienced in this. Now, when you calculate your gradient, of course, you must show your working, and definitely you want to follow the SF significant figures. Okay, so that is definitely the 3 significant figures. Units depends on what your quantities are. Okay. I have one question. What do I do if my points form a curve, but the question has a linear equation for my graph? How do I force a straight line onto it? Your points form a curve, but your equation shows a linear equation. Um, if it's really supposed to be a linear equation, like you say, then it could be that it's not a curve. Okay? You can still find a way to, I mean, you can try to find a way to, because if your plotted points are correct, right? If your plotted points are correct and they need you to draw a straight line graph, straight line, then something must work. Okay? So you have to try your best to figure out how to draw a best fit line from there. If it's supposed to be a line lah, a straight line. Okay? But you can quick glance at your neighbors and see, are they drawing curve or straight lines? Okay, then look around. I mean, don't look so obviously lah. Okay, so glance a little bit, make a decision. Okay. Yeah, it's the reason why we did. Okay, let's look at question B. Now, question B is on a temperature or heat question. Okay, so this part here, let's quickly go through that. So for this, you need to draw the graph. For this, you need to draw the graph. Okay. Now, you should know that neutralization reaction is exothermic. Okay? Neutralization reaction is exothermic. So we are using strong alkali, strong acid. Okay? Now, we are using polystyrene, of course. Okay, for most of your experiment involving heat, right? Okay, you'll be using polystyrene. That is, of course, because it's an insulator, right? It helps to reduce heat loss. Okay. Now, you put this on a glass beaker. Can you tell me why we need to put the polystyrene on a glass beaker? What's the reason for that? Okay. There can be a few reasons actually. Like what some of you said, more stable, prevent heat loss, maybe not prevent, but reduce. Yeah, reduce heat loss. Temperature, temperature not too high say. What do you mean to Okay, but reduce heat loss possible because there's some trapped air inside. But I would say is yeah, it can also be to increase the stability because styrofoam cup they are very light. Without adding anything, they are light. Even if you add some substances inside, it can still be very light and be blown away easily. Okay, so a glass beaker make it a lot more stable. Okay, but other than that is to trap the air and slow down the heat loss as well. Okay, all right. So we have P, which put a strong acid in the burette, measure 40.00 cm cube of P. We are using a burette, right? So two decimal places. Then we record the reading. Okay, next, we use a measuring cylinder to measure 10 cm cube of Q. Pour this into the polystyrene cup. Stir with the thermometer. Okay, we measure the highest temperature reached. Okay, so all this recorded down. Then we empty the cup, rinse with water, repeat the experiment. Okay, now I think you all have some values here. Okay, you all have some values here. So we have the volumes of P, P and Q, initial temperature of P, highest temperature recorded, and the temperature rise. Now there are six errors in these readings. Can you identify the six? Not quadratic lah. Yeah, it's not mathematics. Okay, usually line of best fits. Like two lines of best fit. Yeah. Okay, one of you mentioned is a plus 25, 2.5. Okay, don't need the plus. Okay, just write out your answers, Write out the errors that you have spotted. Then I'll just highlight them here. Okay. So we have the plus 2.5, not needed. We don't need the plus. 30 should be 30.0. Yes, this should be a point zero. One of the initial temperature being 27.0. Yes. Okay, so this is a careless mistake. Of course, if some of these changes, then the rest will follow suit. So if this is supposed to be 27.5, okay, that means that I need to add an extra 34. This should be a point 0.5 as well, and this should be a point 0.5 as well, correct? So they should follow that point 0.5 there. Wait, let me see, sorry, mistake, not this. Highest temperature, let's keep it the same as for that. Then this is 7.5, correct? No, no, no. This is 6.5. This should be a 6.5. Okay. Anything else? 3SF. Rise in temperature. rise in temperature is calculated. No, no. Okay, so I think we have identified a few. Can you all still identify any? Now, 4.8 anomalous, now it depends. Okay, so this highest reading, now there's actually an error here. This is 32.3. So none of you have identified this. 32.3, this is actually 32.5. Why? Because you look at all the other readings, they're either zero point 0 or zero point 0.5, which means that this is a thermometer that is a zero point 0.5 thermometer, not a zero point 0.1 thermometer. Okay, and that will affect the answer here. So temperature rise, okay, that should be 5.0. Okay. Now, and you mentioned the rise in temperature is calculated. Actually, it's not. Now, the main thing is just a difference. If it's just a difference in measured values, that is not considered calculated. Okay, you go back to that page there. Where is that? Yeah, there. If it's average, average is when you do your titration reading, you find the average. Or if it's a difference, and then they should follow the same significant figures. So in this case, it's not calculated. Okay? All right, so we have these errors here, so you take notes. Now, next thing is to plot your points. Can you quickly plot the points here? You're supposed to plot the points, plot the graph of temperature rise against volume of Q. Can you quickly do that? And try to draw the two intersecting straight line. Okay? It might take a while, but I need you all to do a little bit faster there. Now your two straight lines must cut at the they must intersect each other at the highest temperature reach. It should not be it should not be the plotted points. Okay? It should not be the plotted point. Ziyang, you recorded 30.5 and 30. I'm assuming you're using the same thermometer, right? How come it will be different if they're in the same room? That's strange. But if that happens, you record what you see. You record what you see. Okay? Because if you record those that are 30, those that are supposed to be 30.5, you record 30, then your temperature rise might be different, and that might end up as an anomaly. Okay? Because the temperature rise is the important one. Temperature rise is the important one. Okay? Which is a difference, right? So if you try to make sure all the initial temperature are the same when it is not, then your temperature rise might be a bit higher or a bit lower for that reading. Okay, are you drawing your graph? Make sure you are drawing. Teacher Ashikin is here. Let me add her. Okay, while people are drawing, right, let's say hi to teacher Ashikin. Hello. How did your lesson go? Okay, later teacher Ashikin will cover the QA and the planning. Okay. Great. Okay. Q. One of you asked for the measuring for volume of Q two decimal places. It depends on what you're using actually. Because in this case, we are using measuring cylinder to measure volume of Q. So this measuring cylinder could be 1 cm cube. It could be by percent by per cm cube. So then it will just be in there will be no decimal lor. It really depends on which measuring cylinder they are using. So if they are using this kind, only measure up to 1 cm cube, then it will not have decimal places. Okay. Okay, now let's go through. Now, so your graph would look like this. Sorry, not like this. Now, remember when you draw, there are a few things to take note. Okay, I think plotting of the graph not difficult. Okay, you just need to get the correct scale. Your scale should be like this. You see, your scale should be, yes, like this. 0 to 40 for the x-axis. Okay, and 0 to 10 for the y-axis. Maximize all the space already. Okay, but this is not my final answer. This is not my final answer. 2 to 7 for y-axis. 2 to 7 possible. 2 to 7, 2, 3, 4, 5, 6, 7. Degrees Celsius. All right. Now, but this is not my final answer. There's a problem with my answer here. What do you think is the problem? What do you think is the problem? Nobody? Can you all see here? We have a big gap. There will be no units for x-axis. Supposed to be a curved graph. Okay. No. Okay, let me see. Axis unit for x-axis. That there is no units for x-axis. Well, there is a CMQ here. The CMQ is there. What? Supposed to be a curved graph? No, the question actually asks you to draw two intersecting straight lines. So not a curved graph. It may look like a quadratic graph. Please don't draw that. Please don't go and draw your curve, your quadratic curve. Okay, no anomalous point circle. Now, when there's no anomalous point, you don't have to go and purposely put one anomalous point. If there are not supposed to be anomalous point, then don't put any anomalous point, okay? It's okay to have no anomalous point. Yes, it did not cut the origin. Okay, it is supposed to cut at the origin. Okay, so what happens here is if the volume of Q you use is 0, should there be any temperature rise? No, you don't even have anything to start with. How you have temperature rise? So it must cut the origin. Okay, but unless you are not starting with 0, then I think it's fine. If you are starting with 0, then you better go and cut the origin. Find a way to cut the origin. Okay, that means that you must tube your best fit line according to the origin. Okay, so this is the answer. It should be similar to just now that one. Okay, you can see that this line cuts through this point, okay, but 1 point above, 1 point below, about the same distance from the best fit line. Okay, now then the other best fit line cut through only this point and then 1 point above, 1 point below, about the same distance from the best fit line. So you see that these 2 points intersect each other at a point that is higher than the highest reading here. Okay, highest plotted point here. So this is the correct one. Okay, the highest temperature reached, which is 27 here. Okay, so this is 27.0. All right. No, you don't need to extrapolate. Yeah. For y-axis, do we need to point something? Let me just double check. Y-axis is the temperature rise. Temperature rise. Yeah, actually we should put the point something. Yeah, so let's do that. Just put a point something for the y-axis. Okay, so 10.0, 8.0, 6.0, 4.0. Basically, just put the decimal place. That makes it more correct. Oh, I put it the wrong one. Okay, but y'all get what I mean, Just put the point zero behind. Okay, now let's answer the questions. So, first thing, okay, I put a few notes here already. Best fit line must cut the origin, okay, and the point of intersection must be above the plotted points, not exactly on one of the plotted point. Okay, so this is important. Okay, I already read the value. This is 27.0. Okay, hold on. Um, okay, let me stop share. Wait, on. It's hanging on me. Start again. Okay, okay, let's answer the questions. So the reading here, this is 27.0. Okay. Now, calculate the volume of P which reacts with the volume of Q in C part 1. Now, I have Q which is 27.0. Remember, total must be 50 CNQ. Okay, I have 40 with 10, 35 with 50, and so on. So total must be 50 here. Okay, so which means that I simply do a subtraction. Okay, I simply do a subtraction. 50 minus 23, minus 27.0. Now this ends up with a 23.00. Two decimal places. You know why? Because it's added from a burette. Okay, so it goes back to the precision of the instrument that you're using. Okay, it goes back to the precision of the instrument you're using. So two decimal places for that. Okay, so this is 23.00. Yeah. Okay. Yeah, Okay, I want to quickly move on. Now, what are two changes that you would suggest to improve the accuracy of these results? Now, whenever you're dealing with experiment with heat, definitely one important thing is to do what? Just now, actually at the start, I had mentioned something related. You have the styrofoam, and then you have trapped air. All those are for what? Insulation, right? Reduce heat loss. Correct. Reduce heat loss. Thank you. Correct. So same thing here. How can I further reduce the heat loss so that the results are more accurate? Now you must understand if it's uh every time with experiment on heat will be lost quickly. How do I slow it down? Okay, when I slow it down, I can measure the temperature more accurately. That's why I'm making the results accurately. Good. Place a lead. Correct. Okay, so that will be the first answer. Go and place a lead. Any, okay, what else can I do? What else can I do? Not in terms of heat loss anymore. What else can I do? Where got fan? Turn off the fan. You mean the fan in the lab? Uh, but I think just focus on what is given in this setup. Okay? Yeah. Because not supposed to have the fan there also. Okay, what else can we do to improve the accuracy? Okay, so sometimes you can read the question for hints. Okay, sometimes you can read the questions for hints. Repeat the experiment 3 times. That is to increase reliability, may not be increasing the accuracy. Accuracy is what can you improve in your setup and your readings become more accurate. Now there's this step here that maybe no, you didn't really read it. Empty the polystyrene cup, rinse with water. Then I continue to repeat experiment once. Is there something wrong here? Is there something wrong here? Okay, good. Some of you say make sure no water. Need to make sure no water. Use an empty new cup. Dry the cup. Correct. Okay, not that the water reduces the temperature, or it may reduce the temperature, but the water can cause dilution, right? Okay, so we do not want to dilute the mixture. Okay, because the water will just be additional liquid inside. Okay, so we want to make sure that it's dry. So instead of once you wash it, you go and do the next one already. Make sure you dry it or use a new one that is clean and dry. Okay. Now, just like I see one of you mentioned to use a burette to add Q, if I'm not wrong. Yeah, use a burette. It sounds like it's actually increasing the accuracy or the precision. But the thing about using a burette, you see why they use a measuring cylinder is because how do you transfer the mixture? How do you transfer the liquid from the measuring cylinder? Simply pour it in. And the reaction starts. The problem with a burette is it's very slow. Okay? And for an experiment on heat, if you are slow, heat will be lost. Okay? So that is what we are actually rejecting here. I think a lot of students had written this when it came out before. Okay? Use a burette to make sure you measure Q more accurately, more precisely. But it's actually not so helpful because it's slower. It causes a greater heat loss. Your temperature will be different. Okay? Now I give you another possible answer. Now, to increase accuracy, one other thing that you can do, okay, you see this highest temperature is at around 27, right? So why not let's measure more intervals here, around 27, so that the measurements are a lot more accurate. For example, I can measure 25, 26, 27, 28, 29, etc. Okay? So that is another possible answer. Okay? Yeah, of course, it's some they are already diluted. I mean, they are dilute solution. You don't use concentrated solution in your experiments. They are diluted solution, correct, but adding more water make it even more diluted, and that affects your temperature rise. Okay, because making more diluted, you change the concentration, the reactions is a bit slower, less energy is produced, so temperature rise is affected. Okay, can you all take a screenshot here? I need to rush a little bit. I'm rushing for time. Okay, take a screenshot, huh? Okay, this graph is nothing, it's the same one, just to put it there. Okay, let's move on to titration. Now, titration, uh, one main thing is you must be very careful when you're near the endpoint. I think all of you would have tried titration, for the pure students. I think combined students maybe you have already tried as well. Okay? make sure when you're near the endpoint, you must add drop-wise. Okay, and once the indicator changes color permanently, then you stop. Okay, now some common indicators you must know: methyl orange, that is the most important one. Okay, the rest I would say not so crucial, but it's good to know. But most importantly in your experiment is not whether you memorize all this or not. It's about your observation. What colors do you see on the spots? Okay, so that's the important one. Now for the videos, I'll leave it to you to watch. Okay, because the links are there, you can scan the QR code also. I think you can access them. All right, so this first video is on thymosterline. I'll leave it to you to watch. The second one here is using oxidizing agent, potassium manganate 7, okay, on iron 2 sulfates. Okay, so I leave it to you to watch this as well. Okay, these are really good videos to show you different experiments that happen in the lab. Okay, so that you have visually seen it and you will not be surprised when it comes out. Okay, likewise for example 2 on the thiosulfate and starch indicator. Okay, so read through this. Watch the video, I mean. All right. Now, the important parts for titration are the steps. Okay, another important part are the steps. What should you do? So just as someone was asking me, now what should you wash the apparatus with? So remember, pipette, you use this, pipette, you use the distilled water or deionized water, then the solution. Burette, same thing. But conical flask that is below the burette, you only wash with distilled water. Okay? You don't go and wash with whatever solution, just only distilled water. Okay? Now, usually when you pour a solution in the burette, you'll use a filter funnel. Make sure to remove that first before you start your experiment. Okay? And of course, check for any air bubbles. You let it flush out first. Remove any air bubbles because the air bubbles take up some space. Okay? If you don't remove the air bubble, it will affect your reading. Okay? Now, so this is what I mentioned, right? So you flush out some first, remove any air bubbles. Okay? Now, when you top up your burette because of repeated titration, you don't have to top up all the way to 0.00 all the time. Okay? You can top up to any values. But any value, I mean values that are easy to read. Not that you totally cannot. It's not that you totally cannot use 4.6. You can, it's possible, but why not use an easier number to read? Okay, so 10.00 is a very good number. Okay? For pipette, how to use a pipette? This one you practice on your own, and there are a lot of videos online to use the pipette as well. I think there's a video on this. Okay, it could be this. No, this is only to get the last bit out of the pipette. There's a video on pipette online that's very good. Okay, I forgot to put the link here. Okay, they teach you how to use the pipette if you have forgot the pipette filler, if you have forgotten how to use it. Okay, and I think very important one is this point. Usually for pipette, there is a small volume that is left at the tip. Okay. Now, of course, you can get out most of that, but there will be a very, very small volume that you don't expel. Okay. So this video shows you how to get out the remaining volumes, but there should be a small amount that's still left inside, but you can't get it out. Okay. Now, when you do your titration, remember the first one is usually an estimation. You estimate for the first one, you get a rough volume. Then your second and third one should be as accurate as you can because you know it's roughly that volume. Then when you are near that volume for second and third titration, you slow down, add drop wise. Okay? One drop at a time. And that one single drop is going to change your indicator's color. Okay? Record your readings up to 0.05 cm cube. This one I mentioned at the start. And you should only choose the best titration that are within 0.2 cm cube. Okay? If you don't have anything that within 0.2 or even better 0.1, then you have to redo titration. Okay, it takes up a lot more time. Okay, try. Of course, that's why it's important to add drop wise when you're near that volume. Okay, don't want to redo your titration. It's very tiring. How many drops of indicator is recommended? I think no need a lot. 2 to 3 is sufficient. Okay. If you are using very dark colored indicator for whatever reason, then 1 drop to 2 drop is sufficient. If the indicator color is very light, then you can add 2 to 3 drops. Okay? Because if it's very dark, it's already very dark. There's no need to add too much. Okay? If it's too dark, it's very difficult to observe. Okay? Okay, let's try this question. Okay, you read through first, and I want you to fill out the titration reading table. Okay, so assume that these are like your burette. Read them like you would. Okay, so what is inside this burette? Is your Q, which is sodium carbonate. Okay, and in the conical flask is already the sulfuric acid. Okay, do you have it already? Now fill in the blanks as well. Burette reading, write it down. Final burette reading, because some of you just write final, initial, or final reading, initial reading. Write the burette, okay? And the volume of the correct substance, in this case, Q is the one being added from the burette. So write that down. Okay, so first one should be 0.00 for initial reading. Then you see that this is 26.8. Okay, 26.8. All right. Then you see that for second titration, we did not fill it up all the way to the top. We fill it up to 10.00. That's fine. 10.00. Okay, then you have, of course, you must always leave sufficient. You know it's roughly how much you must add until it's sufficient. Okay. So this is 36.4. Okay. Then final one. See if you have gotten this. Okay, final one, we added the 0.00 again. Okay, so how much did we use? So which two should I choose? I think it's quite obvious, right? Okay, it's quite obvious. We are choosing 2 and 3 because again, first one is usually an estimation. Okay, so it's expected is more. Okay, it's more than what we need because we are likely to add excess. Okay, then the second and third one should be slightly less than the first one and a lot closer. So this is within 0.1. Okay, did everyone get this? Can Okay, I'll move on. So with these two values, can you calculate the average quickly on the next page? I think average should be quite straightforward, right? Okay, between 30 and 40, that's just 35. Okay, this one all of you should be able to do. So this one I'll just show the answer. Do I use all the values? What do you mean by that, Joshua? What do you mean all the values? You only choose the two which are within 0.02 plus minus 0.02. So only the best titration results are 2 and 3. All three values of the Q added. No lah. So we only use this and this. We calculate average using the two best titration results, which are within 0.02. So this one we don't. Okay. This is also the question I asked in the Telegram. If some of you are in Telegram, right? Titration reading. They should be within 0.02. You choose those that are very close to each other. Okay. Now we have the average reading. So this is how much Q we have added. Okay. So let's move on to B. Now they say that Q is this concentration of sodium carbonate. All right. Now, I want to calculate the number of moles of sulfuric acid in 25.0 cm cube of P. 25.0 cm cube, this is what was used in the titration. So that is fine. We have the volume of Q, 26.35. We have the concentration. We can easily find the number of moles. Okay, so this is the part where your mole constant and stoichiometry is very important. So if all those you cannot do, then this calculations is basically alien to you. Okay, so please make sure you practice on that before your practical. Practice on your stoichiometry. Okay, so you find the number of moles using these formulas. I have the concentration. This is the concentration. This is I have the volume. This is the volume. Of course, you convert to dm cube. Then I can find the mole, right? Just multiply them together. You have that. So you multiply them together in mole times dm cube. Sorry, concentration times dm cube. You get the mole. Okay. So with this number of mole, what should you do? This is the number of mole of Q only. Going back to the question, you need to find the number of moles of sulfuric acid in 25 cm cube of P. So how do I from Q go to P? Then it goes back to your mole ratio. Okay, so your mole ratio here, your Q is sodium carbonate, right? So sodium carbonate to HX. Okay, so 1 is to 2. So your number of moles must times 2, and that is the number of moles of HX. Okay. Take a screenshot, huh? Okay, moving on. Now, using this number of moles, actually this part B is really just the standard stoichiometry, not too much of a difference. Now, but part C is slightly different. Part C is on this concept of dilation, dilution. Okay, but not exactly that dilution yet. Okay, so I have this number of moles in 25 cm cube of P. But what happens? How many moles would there be in 250 cm cube of P? Okay, this part you must understand. In 25 cm cube, I have this number of moles, but I'm actually not diluting this solution. Okay, they're asking you that if I have 250 cm cube of P, how many moles would there be? It's actually just hold on, oh, wrong number of zeros. Hold on, let me check. Yeah, it should be one more zero here. My apologies. One more zero here. This is what you meant, right? Yes. Okay, so coming back here, so all you need to do is to multiply by 10. Okay, multiply by 10. Okay, 10 is because 250 over 25. Okay, because now I have 10 times that volume of P, so I have 10 times the number of moles. Okay, now you do realize that for all this calculation is unlike the part B. Part B we rounded off to 3SF for the final answer. But if subsequent parts I need to use that value, I must use the unrounded values, which means that I do not go and use 0.00279. It should be 2792, the unrounded value. Okay? Now, so I have the number of moles of HX. I need to calculate the mass. So it goes back to your formula. I have the mole. I want to find the mass. Do I have the molar mass? I have. It's given. 97. Okay, they're all given. Okay, so you have two of the three variables. So you put it on equation, you use the number of moles times molar mass, gives you the mass. Okay? Okay, take a screenshot here and then we'll move on. But we still have QA and planning to cover. Okay, 5 seconds, 5, 4, 3, 2, 1. I apologize to rush you guys. Okay, next one. Calculate the percentage by mass of sulfuric acid in 3.3 grams of descaling powder. Now, for this, you see we have gotten the 2.71, which technically is 2.708 grams. This is the mass of HX. Okay? They ask you for the percentage by mass of sulfuric acid in 3.3 grams. So how many percent is that? Okay, so you just have to do a percentage here. Okay, 2.708 over 3.3. Then that is your percentage. Okay. Last one here. Okay, last one here is like a small planning question, a simpler planning question. Okay, they say that lime scale is formed in kettles where there's hard water, okay, that is used for boiling. So hard water usually contains a few ions, example, calcium and magnesium. Okay, so the thing is, they want to remove this hard water by softening it. Okay, so describe how a beaker of hard water can be softened by using aqueous sodium carbonate. Okay, so I repeat again, the point here is to remove these two ions. Once I remove these two ions, then the hard water is so-called softened. Okay, and I am removing by using this aqueous sodium carbonate. What do you think is the concept here? How do you think this works? If I add sodium carbonate, somehow I can remove the two ions here. What do you think is happening? Displacement. No, not displacement. It's not displacement. Sodium, how can be displaced? Sodium is one of the more reactive metals. It can't be displaced by calcium and magnesium. And calcium and magnesium here are already ions. When we talk about displacement, we are adding the elemental metal to the solution. So this is not displacement. This is not displacement. Okay, you must understand sodium carbonate solution is basically just a solution with sodium ions and carbonate ions. In contact with calcium ions and magnesium ions, what would they form? It is not exactly displacement, but because these ions are free moving, right? These ions are free moving, yes, the calcium ions, magnesium ions will just bond with the carbonate ions. It's not exactly a displacement, but because the ions are free moving, they can come into contact with one another. So calcium ions, magnesium ions, they will just bond with the carbonate ions that are floating around. Sorry, 2 minus. Oops. Okay, so they are just bond with the carbonate ions that are floating around. And that forms a precipitate. Because these two are insoluble. Magnesium carbonate, calcium carbonate, they are insoluble. That's how they can be removed. So if you think along that line, what will happen if I mix them together? I mean, the only other product would be calcium carbonate, magnesium carbonate. These are the only other products that we can produce. And what makes it different is that they are insoluble. Okay, so we can separate them by filtration. Okay, we separate them by filtration. So you describe the steps. It's a simple planning question, but a lot of students will stump somehow. Okay, they were caught by surprise. Okay, you simply add it to the beaker of hard water, then you remove this calcium carbonate, magnesium carbonate, and you collect what is in the filtrate. You collect the filtrate, basically. Okay, but you want to repeat this because you might not have reacted, you might not have removed all the calcium and magnesium ions. So you repeat it again to make sure all of them have been removed. Okay, until no more residue is collected. Okay, explanation is below. Again, you can screenshot this. Okay, can I'll give you 5 seconds to take a screenshot and I'll pass the time to teacher Ashikin. Teacher Ashikin, are you ready? Okay. Okay, I'll pass the time to her now. Thank you very much.
Okay, everyone. Hi. Thank you, Mr. Meng. Okay, so now I'm going to continue with the QA and planning. Okay, so I'm just going to go through it quickly. All right, so if you have any questions, just put it in the chat. Okay, so now, so for qualitative analysis, right, it's basically for your exams, okay, a QA table will be given to you. So of course, you need to memorize it for your papers, other papers, but for exams, practical exams, it will be given to you. So I'm going to show you, rather show you how to manage QA quickly so that you can answer the questions during practical faster and then make less mistakes lah. Okay. All right. The aim is not to make any mistakes. All right. Okay. So first, when you're given a sample, okay, that contains an element, a salt or a mixture of salts, you need to test what kind of ions there are. Of course, that's the basis of qualitative analysis. So there are two types of ions. There's anion and cations, right? So for cations and anions, during the testing, especially for cation, we use, you need to know that, or rather by now you already know that we use hydroxides and also ammonium hydroxides, right? Sorry, hydroxides such as sodium hydroxide and ammonium hydroxide to test for cation. But for anion, it's a bit more tedious to memorize. Okay, so let's look at it. So first, okay, I'm just going to skip through this first. I'm going to show you the table first. What I'm trying to explain here is this. Now, for cations, right, the way to memorize it, or rather the way to expect it when the question comes out, if the question says, oh, test the sample with sodium hydroxide, add sodium hydroxide to it, or add aqueous ammonia to it, and that's it, right? Nothing follows up after that, after adding the sodium hydroxide and aqueous ammonia. We know that it is testing for the cations. Okay, so except all the cations, we do not need to heat it except ammonium anions. Okay, so sorry, ammonium cations. So these ammonium ions, when sodium hydroxide is added to it, it must be followed up with a bit of warming. Okay, so we can expect when the question is given to you and it says, hey, add sodium hydroxide or add aqueous ammonia, then we know that at the back of your mind, you need to know that it's testing for cation. So you do not need to get your Bunsen burner ready or anything like that. No need lah. Okay. Or rather the testing, what lighted spleen, all that, you don't need to expect any gases given off. Okay. So we can chill there, right there. Okay. But when it comes to questions with testing for anions, right? For testing of anions, like for example, this. Okay, I'm just going to show you here, bring your attention to this. Okay, when it comes to testing for anions such as carbonates, such as nitrates, it will give off gases. Okay, and we have to, how do we know that the question is actually testing for anions? Most often than not, they put acids. Okay, if you notice, all of them is addition of acids except for nitrate. Okay, so if it's addition of acid only, no need to warm up or anything like that, then you know it's testing for carbonates. Okay, so at the back of your mind, you are actually testing for carbonates. Oh, okay, so if only acid is added, carbonates, if let's say it is positive for carbonates, you must know that bubbling, you must expect that effervescence will be produced. So like it or not, if there is no effervescence or there's effervescence, please get your lime water and delivery tube ready, okay, at hand, okay, just in case that there will be effervescence, okay. So that's how you can quicken the pace during your practical, because sometimes when you're nervous, you don't have time to finish the qualitative analysis correctly, and by the time you set up all the delivery tube and everything, all the gas is gone, and then you can't get the samples. I mean, you can't top up samples, and samples given to you, the volume is quite small, right? Okay, so we do not want to waste any of the chances of finding out whether it's carbon dioxide or not. Is you must detect, or rather you must what do you call that, expect what you are testing for, okay. Now, so if let's say if you have already tested all of that, okay, and there is no visible changes, you need to write down no visible change or no observable change, okay. If there's no precipitate or no gas forms and nothing at all, no change, no visible change, just write down no visible change, okay. So now let me bring your attention to this part here. When gas is produced, if it's hydrogen gas, we need or oxygen gas, we need to have a wooden splint and Bunsen burner ready, okay. So, and for carbon dioxide, we need lime water and delivery tube, like I've said earlier, okay. And for ammonia gas, for some, like for example, ammonium ions, when you're testing for ammonium ions, a pungent smell will be detected, and we need to get our litmus paper moist it first to get it ready with distilled water at the mouth of the test tube, okay. Okay, next. Okay, I'm just going to go through quickly here. Okay, if you have any questions, please ask. Okay, right. So the difference between nitrate ions and testing for nitrate ions and ammonium ions, right? For nitrate ions, we add sodium hydroxide. Same goes for ammonium ions. But the only difference is that when it's warmed, nitrate ions use aluminum foil, or rather that aluminum foil is added to it. But for ammonium ions, no aluminum foil. Okay, so that's the only difference. Okay, right. Of course, you need, for cations, when you see precipitate, and also anions, when precipitate is formed, you need to record down the color. Okay, the color change, and if it's iron, for example, if it's iron, it's green PPT. If it's iron 2 plus is green PPT, whereas iron 3 plus is red brown PPT. And for cations, you have to add excess of sodium hydroxide or aqueous ammonia to see whether the precipitate dissolves or not in excess alkalis. Okay, so this will give you an idea what kind of ions it is. Okay, right. So for gases, when it's tested, okay, we can expect carbon dioxide to give white PPT with lime water. Hydrogen, using a lighted splint, it will give a pop sound. If there's a presence of oxygen, instead of lighted splint, we use glowing splint. Okay, so glowing splint is basically the stick, the splint, you burn it and there's no flame on it. It's just glowing, okay, like ember. All right, okay. Next. Okay, so if let's say, for example, right, some practicals might test you on flame tests. So, okay, what you need to do, flame test of cations, yes, you do not need to know to memorize the color. Some schools actually, some schools or your teachers might give you a list of colors, but for O levels, we do not need to know it. But when it's given to you, when you are supposed to flame test for cations, you just need to write down what you see. Okay, if it's lilac color, lilac flame, you write down lilac flame is observed. Okay, if it's red, then say it's a red flame is observed. Okay, you just have to write down your observation. That's it. Okay, you do not need to identify what ions they are. Okay, next, adding a metal to an unknown solution. Now, when it comes, what is lilac flame? Lilac flame is like purplish color flame. Okay, right. So adding a metal to an unknown solution. Okay, so what happens to a metal? Usually when No worries. My pleasure, Ryan. Okay, so it could be a displacement reaction or a reaction with acid. Okay, so what happens to a metal? So for example, right, when magnesium ribbon is added, okay, to acid, it becomes smaller, or zinc granules dissolve in the solution to give a colorless solution. Is there any gas evolved? If there is, then you have to write down effervescence is observed, okay? And if you need to test for the identity of the gas, okay? If the gas extinguishes a lighted spleen with a pop sound, you know it is hydrogen gas. But you do not need to write the conclusion yet. You just write down what you observe. Okay, if you observe any change in color, you need to write down fading, like blue solution fades, let's say from copper to sulfate solution, right? Copper ion solution. Gradually, if you see there's a fading or becomes lighter, the blue color solution becomes lighter, then you just say it fades, okay? The blue solution fades or turns colorless, okay? And formation of solid, if you see any precipitate or even gray solid, silver solids forming, or reddish brown solids forming at the bottom of the test tube, you need to write it down. So don't just say, oh, gray solid forms. Cannot lah. Okay, must be in a one whole sentence. Okay, some gray solid forms at the bottom of the test tube. Okay, right? Okay, next. So sometimes questions will ask you to identify the oxidation or reduction questions, right? Okay, or reactions. Okay, so hydrogen peroxide solution, right, is both an oxidizing agent and reducing agent. So every time you are dealing with hydrogen peroxide, if a question comes out with hydrogen peroxide, then you know, hey, this is oxidizing agent. Or maybe it could also be a reducing agent. So you are being tested for oxidation and reduction, or reduction, okay? So you should get ready to test for oxygen gas when hydrogen peroxide solution is used. Yes, when hydrogen peroxide is used, oxygen gas most often than not will be released, okay? Right, so how do we test for oxidizing and reducing agent? First, how do we, rather for reaction with oxidation and reduction, we use oxidizing agent and reducing agent, such as potassium manganate, which is an oxidizing agent. Whereas, what is the reducing reagent? We all know that it is. Can anyone tell me what is the reducing agent the popular one that we usually use? It is potassium iodide. Okay, so that's the reducing agent. Now, so for oxidizing agent is to detect the what do you call that, the presence of reducing agent. Okay, whereas an reducing agent is used to detect an oxidizing agent in the solution. Okay, and so for oxidizing agents such as potassium manganate, we need to memorize that it is purple in color before it gets reduced. Okay, so what happens is that once it's reduced by a reducing agent, it will turn colorless. Okay, from purple to colorless. You must write down observations such: purple acidified potassium manganate solution turns colorless. If you are using reducing agent, right, we need to know that potassium iodide is colorless. Okay, once it gets oxidized by an oxidizing agent, it turns brown due to formation of iodine. Understand? Now, so what about green iron 2 sulfate solution turns yellow, okay, in the presence of oxidizing agent? So this is quite rare, but sometimes, yes, some schools actually test for it, okay, or rather make you test for it. Okay, come, next. Okay, now, so when it comes to heat, when your questions or your exams has heating of a solid, right? It's either heating gently or strongly, okay? So you must read the test carefully, okay? So if aqueous sodium, how do we know, right? So if aqueous sodium hydroxide was added and heating is required, get ready a damp moist paper, red Remus paper, to test for ammonia gas. Okay, so remove the test tube or boiling tube from the Bunsen flame before testing for the gas. Now, you should test for any gas while heating the solid unless otherwise stated. Okay. Now, if water droplets are formed during heating, right, the solid could be a hydrated salt. Okay. such as copper 2 sulfate with 5 moles of water, then sodium carbonate with 10 moles of water. Okay, so this is what we call the hydrated solids. Okay, now next. So what to observe during heating? First is changing of color. Is there any change of color to the solid that we're heating? Okay, so sometimes, example, like this is an example, a white solid turns yellow when heated and turns white again when cooled, such as zinc oxide. Okay, I think we covered this in one of your notes, right? In the one of the topics that we did a few weeks ago. Okay. Next, during revision, yeah. So next is changes in physical state. We need to expect it. Sometimes during heating, the white solid will melt into colorless liquid. And then condensation of water vapor can be observed as well. Colorless droplets of liquid form at the top of the boiling tube, okay? And then if you notice any gases evolved, right, such as carbon dioxide or nitrogen dioxide and oxygen, okay, so carbon dioxide usually is given off during heating of metal carbonates, right? So I think we did this last week, one of the lessons, okay? Some of my students have to memorize it, right? So such as, if you look at green solid, for example, green solid of copper 2 carbonate, turns black while heating because it has decomposed into copper oxide and carbon dioxide is being produced, okay? So you need to write down the observation. Colorless, odorless gas produce forms of white precipitate in lime water. Then we know that it's carbon dioxide. Now, what if nitrogen dioxide is produced? It gives off a pungent smell or pungent brown fumes produced, which turns damp blue litmus paper red. Okay, what about if oxygen is given off? So oxygen gas is colorless. You have to write down colorless, odorless gas produced relights a glowing splint. Okay, what about ammonia gas? Ammonia gas, similar to nitrogen dioxide, they are pungent. Okay, pungent gas produced, which turns on now. It's different. This one we use them red litmus paper blue. Okay, right. So next, give me a moment. Okay, so this is just okay. Sorry. My side is lagging a bit. Sorry. 1 second. Okay, let me just go up. Okay, it's here. Okay, all right. Oops, no, one more. Okay, I hope you're all okay. Sorry, I might drag a bit. I need to cover everything today. Right, Mr. Meng? I'm sorry. We might extend a bit more, a few more
Yeah,
minutes,
because I
okay?
was too long-winded, so I have to extend the lesson a little bit longer. So please
Uh,
apologize for that.
No, it's okay, because there's a lot to cover anyways. Okay, right. So let's look at this example. Okay, this review example. Okay, now questions like this, you see, the question like test number 1, number 2. You look, test number 1. Are we required to test for chlorine gas during practice exam? Chlorine gas, rarely they will ask, but I know for A levels, yes. I'm not too sure for O levels. No, right, Mr. Meng? I don't think so, right? For chlorine gas, no. Okay, so it is toxic chlorine gas. Okay, right. So most of them do not know. Chlorine gas is not tested. But if your teacher has already tested you in the past, then just review on that. Okay, all right. Not all schools will allow testing of chlorine gas because it's not required for all O levels. Okay, right. Next. I hope I help you to answer the question. Okay, now look at test number 1. It's to add aqueous ammonia. The moment you see aqueous ammonia and nothing else, right? No heating, no nothing, just shaking until no further change is seen, you know you are testing for cations. Okay, so you don't need to kanchong take all the what do you call that? The splint, the wooden splint, all that. Chill, no need, because the question didn't ask for any test for an anion, which no gas will be produced. It's just cations, okay? So just expect PPT to be formed, which is precipitate. So in this case, green, for example, this question, green precipitate is formed during the experiment. And when formed, it is insoluble in excess equals ammonia. Then we know, green. We know from the table, we know lah, that it is what, Fe2 plus or Fe3 plus, right? Okay, so if it, of course, it's green. If it's green, it's Fe2 plus, okay? Right. So, next, see, the solution contains iron 2 plus, so Fe2 plus, which is green precipitate. Now, next, the next question says that, or rather the next test is to add sodium hydroxide and warm. Okay, so from the table that we've seen earlier, right, we are testing for the presence of ammonium ions. Okay, so at the moment, you know, it's ammonium ions that we're testing for. Okay, a pungent gas of ammonia will be produced. That should be at the back of your mind. So how do we test for ammonia gas? We have to get the damp red litmus paper ready at the at the mouth of the test tube. Okay, so just get it ready. It should turn the red litmus paper blue if ammonia gas is produced and if ammonium ions are present in the solution. So in this case, ammonium ions are present in the solution. Therefore, it turns, or rather, the pungent gas is produced upon heating or warming. Okay, it turns them red litmus paper blue. Okay. Sorry, I need to go through faster. Okay, so the conclusion is that you have to write down ammonia produced on warming. Okay, next. The next step, test number 3, it says that nitric acid is added, and then after that you need to add drops of aqueous silver nitrate. Then you know that you are testing for cations, because anions we're not doing, we never add acids to cations. Sorry, this is to test for anions. For acids, for cations, we don't use acids to test for it. But for anions, we always use acids to test for the presence of anions. Okay. So in this case, no visible change. Okay. Then next, same thing, dilute nitric acid, and then aqueous barium nitrate is added. Okay. So from the list of table that you will be given, you should know or expect that this test is to test for the presence of barium ions. And in this case, since the solution, not barium ions, it's to test for sulfate ions. I'm so sorry. Okay, it's a test for sulfate ions. So whenever barium is added, right, with an acid, okay, you know that we're testing for sulfate ions, the presence of sulfate ions. If it turns white PPT, or rather white PPT is seen, then you know it is positive for the presence of sulfate ions. Okay, right? So this is something that you need to be more what you need to expect. Sorry, rather you need to know what to expect out of the reactions, okay, or the test. Okay, now if hydrogen peroxide is added, right, you are testing for the presence of oxidizing agent or reducing agent. Okay, now so hydrogen peroxide in this case, it turns the pale green solution, which is Fe2 plus, based on what we know, turns brown. So we know that Fe2 plus has been oxidized. And in this case, effervescence is seen because oxygen gas is produced. Okay. Now, and colorless, odorless gas produced relights glowing splint. Okay. So to the mixture of test 5, next test, aqueous sodium hydroxide is added. Now we are testing for the presence of a new ion that has been formed, okay, which is the new cation. So since Fe2 plus has been oxidized to Fe3 plus from this, what do you call that, clue, okay, we know that it will form red-brown PPT. So if you see red-brown PPT, then you know, hey, that's Fe3 plus. Okay, you can make a deduction after testing it with sodium hydroxide. Okay, right? So the next question is asking, deduce the role of hydrogen peroxide. If hydrogen peroxide works on Fe2 plus and then it converts Fe2 plus to become Fe3 plus, so from 2 plus to 3 plus means it has been oxidized, right? Therefore, hydrogen peroxide is an oxidizing agent, right? So hydrogen peroxide oxidized iron 2 ions in solution X to iron 3 plus ions, or iron 3, as test 6 showed the formation of red-brown precipitate of iron 3 hydroxide. Okay, so just take a screenshot of this answer, okay, because we have to move on. If you have any questions, if you want me to go back to the page before, you let me know. I'll just scroll up later. Okay, take a screenshot. 3, 2, 1. Okay, let's go. Okay, let's move on. Okay. Okay, any questions? Just put in the chat. Okay, let's move on to planning. Okay, planning is like, it's like if you want to cook, okay? If you want to cook, you have to plan what to do, okay? What you want to cook, right? So planning is the same thing. If the question asking you what you are testing for, you need to know the relevant methods, the appropriate setup, the appropriate instruments to use, okay? So first, we need to look at the topics, possible topics that could be tested. First, either gas collection, separation techniques, acids and bases, usually titration question, salt preparation, so on and so forth. Okay, if speed of reaction or redox, sometimes what do you call that? Energetics question will come out too, like, test for whether it's endothermic or exothermic. Yeah, it could be that too. Okay, next, outline a method by describing the procedure to address the aim. So what is the aim of the question, or rather the experiment? What are you finding out? Or rather, what is the question asking you to find out, right? Next, you need to include the independent variable, which is what you can change, okay, or depend, and also the dependent variable, which is measured, and key control or control setup, okay, which is constant variables in your method. So some planning questions may require a control experiment. Yes, okay, so we need to look at the question one by one later, okay? Now, the next step is to state the instruments needed to measure the certain physical quantities and the apparatus and quantities of chemicals needed in the procedure. Okay, so for example, right, we use a thermometer to measure the temperature, right? Or mass balance to weigh the mass of an empty boiling tube. Next is to use measuring cylinder to add about 50 centimeter cube of hydrogen peroxide into a conical flask. Okay. Now, next, use unknown variables for the physical quantities measured if further comparison of a sample calculation is needed. So for example, right, we need to use a stopwatch to measure the time taken for the effervescence to stop at certain time, okay? Or use a mass balance to weigh the mass of an empty boiling tube as M1. So we need to be quite generic when it comes to the unknown with the figures, okay? Because you are explaining on how to do it, but you haven't done it yet, okay? Right, so next is to describe the expected results or observations and give an explanation of how the results could be used to address the aim of the experiment, okay? Next. Okay, let's look at this example question, okay? So this metal carbonate, we do not know what the metal carbonate is. It's MCO3, okay? Now, so decomposes on heating to produce a gas. Okay, so MCO3 gives off MO and CO2, right? Okay, so the MR of MCO3 can be determined by heating solid MCO3, okay? So this is thermal decomposition. This should be in your head already, okay? Thermal decomposition of a carbonate, a metal carbonate. Okay, so outline a method to determine the MR of MCO3 by measuring the loss in mass. In the method, you should include the apparatus used, measurements you would take, and also an explanation of how you would use your results to determine the MR of, or the molecular mass of the metal carbonate. Okay, so you may assume that apparatus normally found in a school lab are available. Okay, so what do we first do? Okay, we are given the metal carbonate, right? First, we need to use a mass balance to weigh a certain amount of MCO3. Okay, in this case, always put small amount. Don't go don't go crazy with the numbers. Some people put 20 grams. Why? At the moment you put 20 grams, 50 grams, the more mass you use, the longer it takes for you to finish the experiment. So make sure you just use appropriate amount, like 1 gram, 2 grams is enough, okay? And add it into an empty boiling tube and reweigh the mass of the boiling tube and its contents. Let this mass be M1. So this is like the initial mass before heating, okay? Next, The next step is to heat the boiling tube and its contents for about 10 minutes. Okay. Now, allow the tube to cool to room temperature before we can reweigh it. So then this is to identify how much of MCO3 has decomposed by heat. Okay. Next, repeat step 2 until the mass remains constant. Let this mass be M2, which is the final mass. Okay. Last but not least is once we've gotten the final mass, and we have the initial mass, right, which is M1, right? We can calculate the mass of carbon dioxide loss by taking initial mass minus the final mass. And then divide by the MR of carbon dioxide or molar mass of carbon dioxide to find the number of moles of carbon dioxide produced, okay? Or rather, yeah, correct, produced, okay? So we can use it to put in the equation, okay? So the number of moles of MCO3 is equals to the number of moles of CO2. So based on the stoichiometric ratio, 1 mole of MCO3, which is the metal carbonate, is equals to 1 mole of, or rather it produces 1 mole of carbon dioxide. Okay. So the MR of MCO3, since the number of moles is the same, you just take 1 divided by number of moles of MCO3. Okay, which is the same as CO2 here, number of moles of CO2. What is this 1? This is actually 1 gram. Okay, the mass of the metal carbonate. Okay, so in this question, right, take a screenshot first, okay? In this question, right, how you answer it, you do not need to write values. Don't say, oh, for example, 3.5 moles of CO2 is produced. No need. You just be generic, like, oh, M1, M2, for M1 for initial mass, M2 is for final mass, okay? And then just give equations like this. You do not need to put numbers in. Understand? Okay, be generic when it comes to writing what do you call that? The planning, your answers, okay? When it comes to calculations, right? But you must be clear at the same time, like MR of MCO3. You just don't like, oh, okay, number of moles of CO2, or rather you just give this only. Then we're like, huh? You're not explaining what this is, you know, you cannot expect people to understand what you're writing. So you must be very clear, really write what, explain what you are finding out. What is that formula for? Like for example, this is for number of moles of CO2. Understand? So the headings must be clear, okay? Right. So next part, let's look at B. A gas collection by the displacement of water can be used to determine the molecular mass of the metal carbonate as shown in the diagram below. Okay. So we know that when MCO3 decomposed thermally to form MO and CO2 is given in the question above. Okay. Suggest how this method may cause your calculated value of the molecular mass of the carbonate to be different from the value in A. Now, this is water displacement. You see displacement of water here? Okay. Now, what gas is produced? Carbon dioxide, correct? You have to think. Carbon dioxide can dissolve in water or not? Is it soluble? That's a question that you need to ask yourself before you answer the question. Okay. It will be slightly lower. The volume of carbon dioxide collected using this method will be slightly lower. Why? Because carbon dioxide is slightly soluble in water. So some of the carbon dioxide molecules have already, or gas has already dissolved in the water. Okay, so the actual number of moles of carbon dioxide will be lower, definitely, because the total volume collected will be lower, correct? Which lowers the calculated number of moles of the metal carbonate. Okay, so when you are calculating the MR of MCO3, it will be greater than in A. Okay, why? Because the volume is lesser. Okay, so number of moles of MCO3 is equals to number of moles of CO2, right? So MR of MCO3 is equals to 1 divided by number of moles of MCO3, which is smaller now in this case, right? So the value of MR will be greater. So then the identity of M will be wrong, right? It won't be accurate. Okay, so this is the answer. Are we all clear? So if you are clear, please screenshot it. Okay. Okay. If you have no questions, if you have questions, please ask away, please. Okay. I'm sorry. I just need to rush. It's 9:15. Okay. Let's look at question number 2. Come on. Okay. In this question, right, is the decomposition of aqueous hydrogen peroxide to produce oxygen gas. Okay. An insoluble powder Z could catalyze the decomposition of aqueous hydrogen peroxide. So a catalyst is a substance which increases the rate of reaction, but it's not used up in a reaction. So why? Because catalysts remain chemically unchanged at the end of the reaction. Okay. Now, given a sample of Z and aqueous hydrogen peroxide, describe a method to show that Z increases the rate of decomposition of aqueous hydrogen peroxide. When it comes to rate of decomposition, a gas is produced. So we need, if you are doing rate, what do we need? Of course, we need to take note of the time. So how to take note of the time? We use the stopwatch. Don't use your phone, okay? Don't go and say phone. So stopwatch. Use the apparatus in the lab, right? The proper apparatus. So at the back of your mind, oh, okay, we need to use stopwatch. Okay, so how do we do it? So Z is not used up in the decomposition of aqueous hydrogen peroxide. That's your clue, okay? So the mass should be the same at the end of the day. Okay, now, so first, how do we measure the rate of decomposition? Remember, oxygen gas is produced, right? So we can trap, no, just kidding. It's not trap, rather we can collect the amount of gas produced. So we can count, we can check or record down how much gas is produced over time, okay? Whether it's faster or slower, that depends on the presence of the catalyst, okay? So first, use a measuring cylinder to transfer about 50 centimeter cube of aqueous hydrogen peroxide at room temperature into a conical flask that is connected to a gas syringe via a delivery tube. Now record the time taken for about 20 centimeter cube of oxygen to form as T1. Okay, the first time, okay, taken. Next, use a mass balance to weigh 0.1 grams of Z. Repeat step 1, but with this Z added to it, okay? Then now we have to record the time taken for 20 centimeter cube of oxygen, the same volume of oxygen collected, okay? So since catalyst is added, we can expect it to be faster because catalyst speeds up the rate of reaction, right? So that's it. That's something that we need to take note of, okay? And record it as T2, the time T2, okay? Then next, filter the mixture from step 3 and collect the residue. So we need to measure the mass of Z, whether it is there any change or not, okay? So wash the residue with distilled water, dry it between sheets of filter paper, then weigh the mass of this residue. So we need to find out whether Z is indeed a catalyst. We need to see whether it is chemically unchanged and the mass should remain the same, right? So if the mass of the residue from step 4 is the same, which is 0.1 grams, and T2 is less than T1, basically the time taken after the addition of Z is faster than T1, which is without the chemical compound Z, okay? Then you can make the conclusion that Z catalyzes the decomposition of aqueous hydrogen peroxide, okay? Right, so this is one way to answer the question because the question is asking us to find out whether Z is indeed a catalyst. So one thing about catalyst is that it speeds up the rate of reaction, and next, it remains chemically unchanged after the reaction. So a setup, or rather the experiment, must include, or rather must find out whether the mass is the same, or whether the time taken is faster when it is added to it. Understand? So what should be kept constant, or rather, what is your the variables that to be kept constant is the amount of aqueous hydrogen peroxide added. Okay, the temperature of the surroundings. Okay, the only thing that you need also the volume of gas to be collected also must be the same. Okay, the only thing that should change is the time taken. Also, addition of Z. Okay, cool. So you can take a screenshot of this. If you have any questions, please put in the chat. Okay. Can I see page 10? Can. Oh my God, page 10. Wait. that's really up there. Wait, give me a moment. I'll just change here to 10. Here? Is this one? Oh, this one Mr. Meng must show you because he's the one with the annotations. Mr. Meng, do you want to toggle your page? Do you want to share your screen? Oops, how do I do it? Oh my goodness.
Yeah, I'll share. Let me share.
Okay.
Yeah.
Oh no, the next one. Okay. Mr. Meng, I think you can share yours.
It's the graph one, right? This one. This is your page 10. Am I
Page
correct?
11, I think. He wants.
Yeah, it's this one.
uh,
Because the student copy is different. Okay, this is your page 10. Do you need the whole page? I think the below part also.
He wants zoom out.
Yeah.
Yeah.
Okay. Okay, any other questions from the students on the ground? Feel free to ask us other than copying the annotations and all. Okay, if there are no further questions, I also do not want to hold you back. D also, okay. Yeah, so thanks for joining us tonight. Okay, I know that it has been a long evening. I also apologize that we have to extend this almost 30 minutes already. 20 minutes, okay, 20 minutes. Okay, but I hope you have learned something and gained more confidence to tackle your practical. Okay, so feel free to, if you see any one of us at the centers, feel free to check in with us if you need to. Okay, yeah, I'm usually at Clementi. So if you
Yeah,
see me, just ask me.
yeah. I'm usually in the North, Sembawang and Woodlands. So if you
Yeah.
see me, you can
Or
just ask me questions as well.
yeah. Or if you all have any questions you all want to send us a message, you all can also wait what's this? If they ask you to add acid to answer that's
Add
unknown
acid.
solid. Okay, I think
Mm,
it depends on the solid. Okay, so I have this student who is asking if you are asked to add acid to an unknown solid in
mhm.
a boiling tube. You have only one sample. How do you know what gas to test for? I think the most common one, the most important thing is to observe that solid. What does it look like? Is it a piece of metal? I think metals are quite straightforward, right? It's a silvery, grayish piece of
Yes, correct.
metal. So
Yes.
you should be expecting to use a lighter splint and already. Yeah,
Mm-hmm.
you have a Bunsen burner, you have a splint ready. If it's a white solid usually would be carbonate.
Yes, correct.
Then you should be testing with lime water. Usually lah. White
Mm,
solids can also be oxides, but I think they usually won't test for oxide because you can't decompose that so easily. Yeah.
correct.
So
You're
you
right.
need you can easily decompose carbonates using heating. So
Mm,
usually that will be carbon dioxide gas.
yes.
Other than that, any other possibility? I don't think so lah.
No.
Unless it's some unknown
Mm,
solids, then they might give you more hints on what to test. Yeah, but
correct.
the two common one to test for acid is definitely a piece of metal or a carbonate.
Mm-hmm.
Yeah.
Yes, I agree. Yes, you just look at the color first, how it looks like to you. If it's silvery, then you know lah, it's metal, then it's hydrogen gas will be produced. Then get all the things ready for that. Okay? So like I've said earlier, yes, although QA table is given to you, you need to familiarize yourself with all the things that is being tested there so that you can do it well during the during the practical exams. Okay? So you won't be too kanchong lah. You won't be too nervous to do it. So, and then after that, you can actually identify the gas produced correctly so that, you can answer the questions properly. Okay? So this is a good question. Yes. It can be any solid. True. You're right. Okay.
I have one question here. If you are messed up in in the experiment, what do I do? Now, first thing, don't panic. If let's say in terms of mess up, if you mean physically messed up, you spilled something, I think you can let the invigilator know, and then if you need to replace anything, get any extra sample, yeah, please check.
Yes.
Let them know. They will give it to you.
Correct.
But if you are talking about experimental results that are messed up, um you judge it yourself. Is it really very messed up? You have you can glance around and see what's everyone doing. Yeah. And you see that oh
Mm,
most people got a certain color, then okay, then you see what you want to do lah. I don't want to
mm,
add scenes lah. But
yeah,
if most people are getting a certain color, then you can decide whether yours is the best. Maybe
yeah.
yours is correct, theirs is wrong also. Nobody knows. But I
Mm-hmm.
would say what you got, then just record what you have. It's okay.
Correct.
Yeah,
Yes. At
even
the
if you
end,
think that yours may be wrong, yeah, just record is fine. And then
correct.
and continue with what you can do lah. Yeah.
You're right. Yeah, I agree with that. So you just record whatever you see. Okay, observe. But if there's no observable changes, just write down observable changes. If the temperature is 25 degrees Celsius, sure, 25.0 degrees Celsius all the way on like that. Okay, so whatever you see, just record. Okay. Now, someone asked, what are the time management for questions like planning? How many minutes? Okay, so for planning, I would suggest about 10 minutes. Okay, 10 to 15 minutes, depending on how well you can process the question. But the best is about 15 minutes. Okay, for the rest, titration, Mr. Mungi, how many minutes should we uh, to allocate for titration? Do you
Okay.
know?
In terms of time management, right? Okay, it really depends on like okay, let's say planning, right? Sometimes the planning can be quite short. Sometimes the planning a bit longer. You need time
Correct.
to think. So like what teacher Ashikin mentioned, I think 10 to 15 minutes is a good amount of time lah. But if it's shorter, then of course use less time lah. So you have
Mm,
more time for the titration. Because sometimes
correct.
titration, if you mess up, then
Mm-hmm.
I mean if you like miss that endpoint, you got a wrong volume, then you might have to redo. Of course, hopefully you do it accurately and try not to redo lah because that wastes a lot more time.
Yes,
Yeah.
you're right.
So
Yeah.
titration, the experiment itself is also
Mm-hmm.
around 15 minutes, maybe.
Yeah.
15
Yeah.
minutes. Is it possible 15 minutes? 15 to 20.
Titration,
I think around there lah.
about 20 minutes lah. 10,
15 to 20,
15 to
20
20,
minutes
yeah.
lah. Yeah, around
Correct,
there
yeah.
for the two times. Yeah.
Mm,
But of
correct.
course, I mean, you have to practice. If you can, you practice. I mean, if your school gives you the opportunity, you practice and
Yeah,
make sure
correct.
you go through that process
Uh-huh.
before your practical. You go through all the steps. If you need to, YouTube is all your friend. YouTube is your friend. You can go and review how to do how to prepare your prepared burette and all those. Do that so that you mentally prepared for the practical itself. Okay. Yeah. Commonly tested topics. Uh, Commonly tested topics. A lot of
Yeah,
times it will be like redox kind of redox
correct.
kind of titration, redox
Mm-hmm.
titration. Yeah, it may
Mm-hmm.
not be acid related. It could be some redox titration. That I think that is quite common nowadays. Yeah,
Yeah, I agree with that. It's usually redox titration because they can ask a lot more questions, lah, I would say. Yeah, but it can be something different. It could only be acid-base titration, a simple one. Yeah, so it depends on your I would say luck lah. But over the years we see a lot of redox titration. So yeah, I have to agree with Mr. Bengi.
yeah, correct. I would say that's the easiest to identify like in terms of trend. The rest QA all these hard to say because QA they can really just give you anything. Yeah, so you just record whatever observation you can see. Okay. So I think we will end the session here. Thanks everyone for joining us tonight. Okay, if you have any further question, I already placed my number in the chat. Feel free to check with me anything. Okay, if you need help for your paper 2, paper 1, just do it. Okay, I can help you. All right. Okay, that's all and have a good rest tonight. Thanks for joining us and hope to see you in our bootcamp. Yeah.
Yeah. See you. Bye
Okay,
bye.
bye-bye.